Hello everybody and welcome to Science Live. We're coming to you again from the Creation Museum here in the Creation Education Lab. And I'm Mr. Roger Patterson, joined again by Dr. Georgia Purdom. And it's a beautiful sunny day outside. We're hearing the geese honking on the pond, enjoying those sounds. We are planning to keep bringing you these broadcasts for quite a while now. So that means I want to get some feedback from you guys about what questions you would want me to answer. So next Friday for our broadcast, I'm going to pick several, 2 or 3 or 4, depending on how long they are, questions that people would send in. So if you comment on this video, things that you would like me to answer and maybe that I could demonstrate for you. I've always wondered how this works, or what would happen if I did this? And I will try to pick some of those that we can answer for next Friday.
Fun.
And we'll get some of your viewer feedback and enjoy doing some of those demonstrations with us. Who we got joining us today?
Well, we have Oklahoma so far, but we got about 100 people here. So
okay, great.
They're getting on.
Okay, today, if you saw the title of the video, it's Dancing Metals. Okay, so this doesn't have anything to do with music or anything like that.
The salsa.
Okay, this is, we're going to look at some different metals. So when we think about the term metal, you probably think of something like an iron or a steel. So like this pair of tweezers would be made out of metal. But if we think more broadly, we look at the periodic table of elements. This is our favorite thing to look at here. So everything over here in the blue and the green, and if you see this little stair-step line across here, basically everything in there are classified as metals on the periodic table. So metals is a very big class of elements. And when we think about metals, they have certain properties. We say that they are typically malleable. You can shape them and bend them. We say that they are reflective. So if we look at a mirror, the backing of a mirror is made out of silver.
Right.
So there are different properties that it has. They conduct electricity. And all of those things are properties that are common to them. So we group them together and call them metals. All right, so we're going to look at some metals today. And then toward the end, we're going to show you the reactivity of all of these things. Okay. Common metals you would have around the house. This is copper. So these are little copper turnings. So you would have copper in your home. Maybe if you peeked under your kitchen or your bathroom sink, there would be some copper pipes. And copper works really good for working with water, because when we dunk copper into water, it doesn't really do anything. It's not reactive. We don't see any bubbles or anything happening there. It's a pretty stable substance in water. So it works good for pipes in our house.
Right.
Okay? Another substance that's has a very low reactivity is the substance zinc. Okay, so if you have worked with your dad building things or anything like that, you might be familiar with different screws that are meant for outdoor use. We say they're galvanized, and that comes from that Italian guy, Galvani, we talked about in electrochemistry, but they're plated with zinc because zinc does not corrode. Okay, so corrosion is a term that we talk about when we say an oxygen in the air, oxygen molecules in the air interact with the metal, and they get this crusty finish over them. So if you think about rust, rust is when metal, iron metal corrodes or oxidizes. So corrosion and oxidation are kind of the same type of term. You can see this still looks pretty shiny. It's a shiny metal, so it doesn't corrode very easily. So it works good if we take an iron screw and if we just use that, it would interact with water and air and rust out very quickly. If we coat it with zinc and galvanize it, it doesn't tend to do that. So we can take advantage of those properties to preserve those screws and make them last longer.
And Roger did not say Zenica, he said zinc.
Zinc,
okay.
yes.
It's not some weird metal we just invented.
No.
It's zinc.
Zinc, so that would be element Zn on the periodic table. Okay, this is aluminum, and this is in a form of little pellets. You probably don't see it like this very often, but aluminum is a very lightweight metal, but it's very strong. So it works good for things like building airplanes out of, because it's got good structural strength, but it doesn't tend It's not very heavy, so it's a low density.
So is this what aluminum foil is made of?
Sure. Aluminum foil, which we often call tin foil, because way back in the day, probably when your grandparents were kids, we used tin to make foil sheets out of, but because aluminum was extremely expensive and hard to produce, but newer technologies have made it easier to produce. So aluminum foil would be this stuff smashed out and spread into sheets. And I could probably take a hammer and pound this out and pound it into a thin sheet like that.
We have someone watching from Berlin, Germany.
Oh, there we go.
That's cool.
That's fun.
Yeah.
Okay. This is a metal called magnesium, not something that you'd find very common. Some of you may have, if you look at your multivitamins or supplements you take, might have magnesium in them. So it's one of the trace minerals that our body needs to survive. And magnesium isn't used for very many construction things or building projects because it's very weak. I could take this piece of magnesium and rip it apart with my bare hands, just like that. Okay, it's not very strong.
Yeah.
And that doesn't mean I'm strong. And it's not very reactive in water either. Okay, it's not going to do anything amazing when I dunk it into water, but it is reactive in weak acids. So it will corrode very quickly in even something like vinegar would make it react and bubble very quickly. So not a good choice for a building material because it's going to interact with the air and acids in the air and corrode very quickly. Any questions coming in yet?
Not so far. Just everybody, we got lots of states represented. Indiana, Wisconsin, Illinois, Wyoming, New York City from quarantine, Michigan. So lots of places
All
joining
right.
us.
Okay, so metals are used in tons of different ways for lots of different things. Electrical conductors in circuit boards in the wiring in our house. You think about the knobs on these cabinets and handles. You can tell they're different colors and different finishes. All of those things we use the different properties of the different metals God's created to accomplish different tasks. Okay, so we think about them as tools in different ways. So all of these things are the intrinsic properties, the properties that they have inside of every single atom. So we talked the other day about the uniformity of nature. So if I got a piece of copper from anywhere in the universe, from Mars, if there were copper on Mars, or for some planet on another star system, it would be copper.
Yep.
It's always the same because God's created them in this uniform way. So when we think about these things, we have different reactivities and different properties. We're going to look here at some fun ones. This is a little jar of something called lithium and sodium. And we're going to put our safety glasses on now. We have inside of these jars are little cubes of lithium and sodium, and they're stored inside of mineral oil because they're extremely reactive. So I'm going to grab one of these little sticks out of here, if I can get it. Okay, and see it's a little chunk of that, and looks like a little rod, and it's not very heavy at all if we tried to pick that up. But different metals react in different ways. Just like I said a minute ago, aluminum doesn't rust very much and zinc doesn't rust very much, but iron really does. It oxidizes quickly. So there's oxygen in the air around us. And the likelihood that a metal is going to react with the oxygen in the air has to do with a property we call electronegativity. Now, oxygen is an electron bully. It likes to steal electrons away from everybody else. Okay, we say it has a high electronegativity. And sodium and lithium have a very low electronegativity. So they tend to give away their electrons. So in chemical reactions, what's happening is you have one atom taking electrons away from other. And if I gain more electrons, and electrons are negative, I become negative. And if I take something's electrons away, it loses its negatives, so it becomes positives. What's going to happen to a negative object and a positive object?
They're going to attract.
They're going to attract. And that's what forms those chemical bonds. And sometimes one totally steals the electrons, and sometimes they share them, and there are different ways to talk about that. We call those ionic and covalent bonds. But what we're going to do here is we're going to bring the camera in close, and I'm going to show you how soft this lithium metal is. So here's my pocket knife, And
somebody just asked if we're going to put this in water, and the answer is
in a minute. Okay. I'm going to slice off a little piece of this here, and you'll be able to see it's very soft and it's very shiny right there on the surface. And in a matter of seconds, it goes oxidized. And now it looks like it's all gray again on the surface. So I could scrape away some of that, and you'll see the shiny, and then it will go away very quickly. So this is a very reactive metal. Okay? It reacts very quickly. So I'm going to take this little tiny piece that's here on the blade of my knife, and we're going to put it inside of this beaker of water. Now, Dr. Purdham's going to slide back just a little bit, just in case we don't expect anything major to happen here, but this is going to react extremely rapidly with the water, and you'll see it fizzing and bubbling all over the place. You can see a little bit of the gas bubbles being liberated there. So this is why we termed this dancing metals. It's reacting so quickly that it's heating it up and it's melting it into a little ball, and that ball is reacting and dancing around the surface of the water.
Okay, somebody asked a question. Which is stronger, ionic or covalent bonds?
That depends on what you mean by stronger. In general, we'd say that ionic bonds are relatively weak because we can put substances like salt. Salt has an ionic bond. We can put it into water and it will break those bonds apart. So they're relatively weak, but they form very strong crystals.
Right.
So there's different ways to think about that. Covalent bonds tend to be much stronger, so it takes more energy to break them.
Like sugar. If you put sugar in water, it just won't break apart unless you heat
all the
the water
molecules
up.
will stay together.
Right, they'll stay together because those are covalent bonds.
Yeah.
So.
And so, like when we light the burner later, that's butane. That's a covalent bond. There's so much energy in those bonds when we break them, it creates a lot of heat, and that'll get up to about 2,600 degrees Fahrenheit.
And no, we're not putting that whole thing in the water.
No, we're not throwing the whole
because
chunk
we would
in the
have
water.
a huge reaction, and we don't want that. So.
Okay, so if we think about lithium here on the periodic table, lithium is up high on the chart here. It's in period number 2. We're going to move down to sodium in period number 3. Now, generally, as we move down a column with the metals, they get more reactive because their electronegativity goes down.
So I'm going back again because I know what's going to happen.
Well, it'll take just a second here. We're going to put this back into the container of oil. Keep it safe. And we're going to pull out a little chunk of the sodium cube here. Now this will look a little shinier on the surface. So we have some little lumps of sodium. And I'm going to handle this one a little more carefully, not use my fingers. You can tell it has kind of a gray coating on it, but if I scratch the surface, if I can get my tweezers around there, if I scratch the surface, it looks very shiny for about 2 seconds.
Yeah, really
and then
fast.
it reacts very quickly. So I can scratch that oxidation layer off the surface and see a little bit of shine, and it goes right back to normal.
Okay, somebody asked, do the reactions of different metals determine how they are used?
Absolutely, because we want to match the properties of the metal with the uses for them. Like I mentioned with iron. Iron works okay for nails and screws indoors, but if we put them outdoors, they would tend to rust out very quickly. So we typically coat them with something like zinc or dichromate things.
Yes, the camera guy has glasses on.
All right, come back in here. We're going to cut off a little chunk of the sodium, and hopefully you'll be able to see that shiny surface under there. And it goes away very quickly. All right. Now I'm going to take this chunk of sodium and drop it in the water, and we're going to watch it dance around the surface. Now I would predict, because of its placement on the periodic table, that this will be more reactive. And indeed, you see it bouncing around much more vigorously. A lot more gas being liberated off of there. That's hydrogen gas and water vapor mixing up there, and we'll try to blow that away from us. And right at the end here, we might get a little pop. Come on. And get smaller and smaller as it's reacting with the water. And a little fizzle out there right at the end. We'll blow that gas away.
Right over on me.
Okay, I'm going to put that back inside of the container for now. So we can predict the reactivity of metals based on where they're at on the periodic table.
Somebody asked from the herb kids, why does magnesium start a fire when it's hot but not to water?
Okay, so magnesium is something that we use to put in welding rods that they weld with underwater. It's used in cannon fuses that are waterproof. Don't ask me how I know that. It's used in fire starter materials because it's pretty reactive. This piece of magnesium strip that I have here is oxidized very much on the surface. I could use a piece of sandpaper and make it shiny, and it would oxidize in a matter of minutes. Not quite as fast as the others, but then when it reacts with oxygen, it has a very vigorous exothermic reaction, so it puts off a lot of heat. And I do hope one day to do a magnesium burn for you guys, because that's very fun.
Yeah.
Hey, we'll get to that someday. Okay, so what we're going to do next is think about producing different gases and things. So you saw the vapors coming off when we put the sodium inside the water. We're going to do that on purpose this time, but we're going to use something a little stronger than water. This is a little flask that's filled with very concentrated hydrochloric acid. So at this point, I am going to the gloves because I want to make sure I'm safe and not get any burns on my skin. I'm going to put some zinc metal inside of here, and the zinc is going to react with the hydrogen chloride. That's hydrochloric acid. So we've got a zinc atom and a hydrogen chloride molecule, and the zinc and the hydrogen are going to trade places because the zinc the chlorine is going to more easily take away the electrons from the zinc than it can from the hydrogen. So it's a simple matter of physics of which one's easier to take away. So the zinc is going to steal the chlorine, and we're going to make zinc chloride. And if there's hydrogen left over all by itself, it tends to form into little molecules of hydrogen gas, H2. Not H2O, that's water. And hydrogen gas. And that hydrogen gas is going to come off as bubbles. So we're going to try and capture that gas inside of a balloon. Now I've inflated this using a little balloon pump and got it all stretched out so it's a little sad looking. Okay, but we're going to put this on top of the flask, this Erlenmeyer flask, after I drop the zinc in, and we're going to watch the reaction here and try and capture that gas. Let me get all my pieces ready. You can see that gas bubbling out of there. We're going to get this on here as quickly as we can, capture that. You can see already we're getting that balloon to inflate. All right. Now, we talked the other day about gas pressure and how different gases act when they're under pressure. So here we have the gas inside the flask bubbling up, and it's being captured by the balloon. Now, it's not going to get very big because there's not enough pressure inside of here to force the latex rubber in the balloon to expand. So this is another way we could look at temperature and pressure and all of those pieces like we talked about with our gas lab the other day. So we're going to give this a minute to react, and then I'm going to prove to you that there's hydrogen gas inside this balloon. Okay. Now, if you were with us several weeks ago, we did what we call a splint test. We used hydrogen peroxide, and we got oxygen bubbles to come up, and then we blew out a burning splint so it was glowing, and we put it in, and it ignited the stick because the oxygen concentration was very high. Okay? And we're going to do the same thing with this, but what do you know about hydrogen gas? Anything interesting?
It's flammable.
It's very flammable, okay? So you can imagine what's coming next because you saw me with the fire yesterday.
Yeah, well, think the Hindenburg, right?
Okay.
So the Hindenburg was this gigantic, what was it, back in the...
A blimp.
The blimp, yeah, back in the...
It's probably early or late 30s.
Late 30s,
I don't
that's why I was
remember
thinking
the exact
30s.
date,
So it was filled with hydrogen gas, right? And as it was coming close to the ground to land, there was somehow a spark that ignited the gas, and you can watch videos of it online. I mean, sadly, it killed a lot of people.
Yeah.
And because it's flammable, and so we don't use hydrogen gas for blimps anymore.
Yeah. So if you think about the Goodyear blimp or those blimps that fly around sporting events, they're now filled with helium gas instead of hydrogen.
Yes.
But back then, hydrogen gas was pretty easy to make.
Yeah.
It was easy and cheap to make. So if I wanted to make money flying passengers from Europe to the U.S., it was a cheap way to do it.
Right.
The problem was it created a really high risk. And that's why we have to consider the materials that we're using in any situation, whether they're going to be the right materials for that situation. Okay, I'm going to pull this balloon off of here. The other thing, my fingers are getting very warm right now because this is what we call an exothermic reaction. We'll use that word a lot. You can feel the heat coming off of there. We're getting lots of heat coming off of there. I'm going to tie this up and set the flask off to the side. And then we are going to see if we can make a little miniature Hindenburg, but thankfully without the loss of life in this case. Set that back there. If you want to get the burner set up there, Dr. Perdeman, go ahead and light it. We're going to move these papers out of the way. Okay.
I'm moving.
She's getting out of the way. I'm going to tape this balloon to the end of this meter stick so I can stand back out of the way. And I'm going to bring this hydrogen balloon close to the flame, and we're going to watch what happens and see if this really is hydrogen gas inside of here. And indeed, we got a nice little explosion. So we know that was a flammable gas. Okay? It had so much force that it blew out the flame. And the balloon here is very warm from that. Okay? So let's make a prediction. I've got another balloon over here. My little smiley face balloon that we used as the sun the other day with Dr. Faulkner's demonstration. I'm going to tape this to our meter stick. Now, kids at home probably know what this balloon is filled with. It's not filled with hydrogen gas, but it's filled with helium gas. So let's make a prediction about what we think is going to happen. If hydrogen gas exploded and made this big fireball, how big of a fireball do you think this helium balloon is going to make? Okay, so go ahead and light the flame, and we'll hit the lights again.
Oh, is it on? Okay. Oh, come on.
There we go.
There we go.
Okay, so make a prediction about how big you think the explosion from this helium balloon is going to be. Okay. 3, 2, 1. Nothing. Nothing happened. That was pretty boring. The Mylar would catch on fire if I did it for too long, but we've got a hole in there. And
if I extract that gas out of the balloon, I start talking really funny. So there's another proof that that was actually helium. If it were hydrogen, I think we would have had a giant fireball and my eyebrows wouldn't be here anymore.
And you'd be in really big trouble.
Why are you laughing at me?
Because you sound hilarious. Right
and Dr.
now.
Rivera gets really mad if I make marks on the ceiling, so I
Yes,
have to be
she
careful
does.
about that.
Yeah.
Okay, so that balloon did not ignite, and I hear my voice coming back to normal now.
That's good.
That balloon did not ignite because it was helium. And helium is what we call an inert gas. It doesn't react. We also call it a noble gas. So we use different gases for different purposes, just like we use different metals for different purposes.
So helium's good for those blimps to use because it's safe, and we don't have to worry about loss of life as a result of that. So somebody said when that balloon popped, they said it scared them because they had their headphones on.
Oh.
Yeah, I gotta warn you, that's loud. So,
yep, the loud pop. So that tells me there was a very rapid reaction there that forced that air out very quickly, and then the air comes back in to fill that space and makes that noise.
Somebody said a lot of these things that we're talking about today sound like a lot of the nutrients that our bodies need. Is there any relationship?
Yeah, we use lots of these. Our body needs lots of these in trace amounts. So, for example, iron we would find in hemoglobin. That's the core of the hemoglobin molecule, and you need lots of iron in your diet to maintain that so that you have a healthy blood system for red blood cells especially. Yeah, so all of these are needed by our bodies in trace amounts. So if we eat a good balanced diet with a variety of fruits and vegetables and foods, we should be able to get all of those types of things. And where we can't, we have supplements that we can add to those things.
Somebody wants to know why helium does that to your vocal cords.
We're going to save that for another day. We definitely want to talk about that, but we're going to save that answer for another day.
Okay.
All right, we thank you guys very much for joining us today. We hope that was a little exciting for you, and sorry for blowing somebody's eardrums out.
They'll survive.
All right, we've got more programs coming up today, so if you keep an eye on Ken's Facebook page and also broadcasting on the YouTube channel, we've got things coming up today at noon and 3 and 7, and we'll hope you'll tune back in to check those out and come back to see us tomorrow. And until then, get out and explore God's great creation.